Imagine for a second, right, that you could that you could breathe into a glass jar.
Okay.
You breathe into this jar, you set it on your windowsill in the morning sun, and then you just leave. You come back a few hours later, and you find it half full of liquid fuel.
Just from sitting there.
Right, exactly. Yeah. And we're not talking about a metaphor here for you, the listener. It's not some abstract unit of energy that, zips onto the electrical grid and just disappears into the ether.
Right.
It is an actual physical liquid, something you could literally pour into a tank and use to, run an engine or heat a house or power a generator when the grid goes dark.
And you didn't plug anything in?
Exactly. You didn't plug it in. You didn't monitor any software on your phone. You just let the jar sit there doing exactly what every blade of grass and basically every green leaf on the planet does every single day.
I mean, it sounds like science fiction, or honestly, maybe alchemy.
Yeah, total alchemy.
But it is fundamentally just chemistry. And the reason we are starting with that specific image today is because of a breakthrough that actually happened in a real laboratory.
Yeah, at Osaka Metropolitan University.
Right. It's documented in a paper they recently published in the journal EES Solar.
Right. And usually, when we cover a new tech paper on this deep dive, we kind of rip right into the market implications.
Oh, always. When is it scaling? Who is buying it?
Exactly. We try to pin down exactly when this is going to disrupt the energy sector, what the efficiency numbers are, how much it costs. But the author of our companion source today, which is this really beautiful excerpt called The Leaf That Needs No Manager, from a broader book called The Intelligence of Inner Order, they explicitly ask us to do something entirely different here.
Yeah, and it's a refreshing change of pace, honestly.
It really is. The author literally calls this a wondering held open. Now, I know that sounds a little, like a guided meditation retreat or something.
A little esoteric, maybe.
Yeah. But the underlying point is actually crucial for us today. We aren't here to declare a winner in the renewable energy race. We aren't making an argument or taking a side.
Right, because this is not a finding or a hard policy position. It is just a wondering.
Let's avoid the trap of treating a lab experiment like a finished consumer product that you can go buy at Home Depot.
Exactly. If we immediately demand to know, the profit margins and the global rollout strategy, we miss the actual genius of what these researchers achieved. Because the Osaka team built a device specifically, it's an electrolyzer that produces a liquid fuel called formic acid.
Which we'll get into, because that alone is fascinating.
No, it is. But the fuel isn't even the most revolutionary part. The spark, the real paradigm shift here, is how the device operates. It learned to steady itself through its own physical nature.
It works with absolutely nothing managing it from the outside.
Nothing. No microchips, no software algorithms, no external battery pack. It just is.
A machine that manages itself just by being what it is. And that is the core premise we're going to explore with you today.
We invite you to just slow down a bit for this one.
Yeah, just breathe with this idea. Follow where it opens or, let it rest. We're going to focus on what might be rather than a rigid, here is what's true kind of debate.
Because there are no sides to take here. We are just going to look at the deep science of how this works, why our standard approach to engineering is completely obsessed with micromanaging nature, and what it would actually mean to build a world that governs itself from within.
So, buckle in. We are going deep into the chemistry, the physics, and really just the sheer weirdness of self-regulating systems. Let's start with the baseline, though.
Right, the fundamentals.
What exactly is an artificial leaf? Because I feel like we need to understand the mechanics before we can really appreciate the philosophy.
Well, to understand the artificial leaf, you really have to look at what a real leaf does. Photosynthesis is arguably the most important chemical reaction on Earth.
Without a doubt.
A plant takes sunlight, it takes water from the soil, and it pulls carbon dioxide right out of the ambient air. And using the energy from the photons of light, it literally tears those water and CO2 molecules apart.
Just break the atomic bonds.
Exactly. It just rips them open. The oxygen is spat back out as waste, which, is great for us since we breathe it, and the carbon, hydrogen, and oxygen are stitched back together to form glucose.
Sugars.
Right. Sugars, carbohydrates, it's physical matter that stores energy.
So it's basically capturing a fleeting moment of sunlight and locking it in a molecular vault.
That's a great way to put it. Now, contrast that with human technology. We are very, very good at capturing sunlight using photovoltaics, right? Standard solar panels.
Sure, they're everywhere now.
But standard solar panels don't make matter, they make electricity. A photon hits a silicon atom, it knocks an electron loose, and that electron flows down a wire.
Right.
but that flow is inherently ephemeral. If you don't use that electron the exact millisecond it is generated, or if you don't have a massive, incredibly expensive battery ready to catch it, it is gone.
It just dissipates.
Yeah. It's capturing energy, but not storing it chemically. The artificial leaf is humanity's attempt to skip the battery entirely and go straight to chemical storage.
We're trying to build a machine that does the glucose trick, but, for industrial fuel. Like trying to bake a cake where the ingredients are literally just light, your own breath, and water.
Exactly. And the specific device the Osaka team built is called an electrolyzer.
Let's break that down for the listener, because that's a term that gets thrown around a lot in green tech. How does an electrolyzer actually turn light and air into fuel?
At its most basic level, an electrolyzer is a device that uses an electric current to drive a chemical reaction that otherwise just wouldn't happen on its own.
It needs a push.
Right. It's essentially a battery running in reverse. In a standard setup, you have an anode and a cathode, 2 electrodes, sitting in a solution separated by a membrane. When you apply electricity, you force water molecules to split into oxygen gas and hydrogen ions.
Okay, wait, stop right there. Because historically, when people talk about the future of green energy, they talk about hydrogen.
The hydrogen economy.
All right, you split water, you get hydrogen gas, you burn the hydrogen, and the only byproduct is water again. It sounds like a perfect closed loop. So why is this Osaka device making something called formic acid instead of just sticking with hydrogen?
Because hydrogen, frankly, is an absolute logistical nightmare.
Is it?
Right. Oh, it's terrible. Yes, it's clean, and yes, it's incredibly energy dense by weight. But by volume, it's a disaster. It's the lightest, smallest element in the universe.
Oh, right, because it's just 1 proton and 1 electron.
Exactly. So to store it in any useful quantity, you either have to compress it to massive, terrifying pressures like 10,000 pounds per square inch, or you have to chill it down to near absolute zero so it becomes a liquid.
Which takes a ton of energy just to do.
A massive amount of energy. You're spending energy just to hold your energy. Plus, hydrogen is notoriously leaky.
Because the molecules are so small.
Yes, they are so tiny they can literally slip between the atoms of solid steel tanks.
Wait, really? It passes through solid metal?
It does. It's a process called hydrogen embrittlement. As the hydrogen atoms force their way through the metal lattice, they actually weaken the steel over time, making it brittle and prone to cracking.
That is, I rember reading about hydrogen embrittlement a while ago. It's like trying to hold water in a sieve made of chain link fence.
Exactly. So hydrogen is incredibly clean, but it's a diva. It demands highly specialized, extremely expensive infrastructure. Enter formic acid.
Right, formic acid. Now, this is where it gets weird.
It does. Chemically, formic acid is HCOOH. It's the simplest carboxylic acid. And fun fact, the word formic actually comes from the Latin word for ant.
Formica, right.
Right, because it was originally isolated back in the 1600s by naturalists who were distilling large quantities of crushed ants.
Just boiling ants.
Yep. It's the exact chemical that causes the burning sting in an ant bite or a bee sting.
So just to be clear for the listener, we are talking about powering the future with ant venom.
In a way, yes. But, industrially synthesized, not from actual ants.
Right, right.
And here's why formic acid is an absolute miracle molecule for energy storage. It is a liquid at room temperature.
Oh, wow. So no 10,000 PSI tank.
No pressurized tanks. You don't need cryogenic cooling. You can store it in a regular plastic vat. You can pump it through standard pipes. You can transport it in normal tanker trucks that we already have driving down the highway.
That solves the entire logistical nightmare right there.
It does. And most importantly, it acts as a phenomenal carrier for hydrogen. When you want the energy back, you can either run the formic acid directly through a specific type of fuel cell to make electricity, or you can easily run it through a catalyst to release the hydrogen right at the point of use.
So it's basically a chemical straitjacket for hydrogen.
Exactly. It holds the unruly hydrogen molecules in a stable, easily managed liquid form until we actually need them. And the way the artificial leaf makes this is by taking the hydrogen ions it stripped from the water and combining them with ambient CO2 from the air.
Wait, so it's pulling carbon dioxide, the greenhouse gas, causing climate change right out of the air to make...
Yes. It achieves 2 massive environmental goals simultaneously. It captures ambient carbon dioxide, pulling it out of the air, and it uses it to stabilize hydrogen into a usable, transportable liquid fuel.
That's incredible.
And we've actually known how to do this in labs for a while. We can build these electrolyzers. The underlying chemistry works.
And this is a massive but, right?
Yes.
If we've known how to do this, why aren't there vats of formic acid on every rooftop right now? The text points out that these artificial leaves have historically suffered from a fatal flaw.
A very persistent one, yeah.
And it's a flaw that honestly reveals something really deep about how humans approach engineering and how we traditionally try to conquer nature. We are utterly obsessed with perfectly controlled environments.
We really are. The flaw is intermittency. Nature is not a laboratory with a constant, perfectly calibrated LED light source. In the real world, the sun moves across the sky, clouds roll in, the wind blows dust over the solar collector, humidity spikes and crashes.
And this is a massive problem for the delicate chemistry happening inside an electrolyzer.
It is a huge problem.
I want to challenge that, though, because if I'm listening to this and I'm not a chemist, I might think, okay, a cloud passes over the sun, the light dims, so what? Doesn't the machine just make a little less fuel for a minute?
Right.
Why is that considered a fatal flaw?
It's a great question, but it assumes the chemical reaction is linear, like a dimmer switch on your dining room wall.
Right, you turn it down, it just gets a little darker.
But chemistry doesn't work like that. Chemical reactions require specific activation energies. Think of it like pushing a heavy boulder up a hill. If you don't push hard enough to get it completely over the crest, it doesn't just go slowly, it rolls all the way back down and crushes you.
Oh, wow. Huh?
In an electrolyzer, if the voltage from the solar panel drops because a passing cloud blocks the sun, it might fall below the strict threshold required to split the water and reduce the CO2.
So the reaction just completely stalls out.
Worse than stalling out. In a lot of these catalytic systems, if the voltage drops to the wrong level, parasitic reverse reactions can start happening.
Wait, reverse reactions?
Yeah, the system might actually start consuming its own products, or the highly specialized, super expensive catalysts on the electrodes might start degrading and oxidizing. The system loses its tune, basically. If it operates outside of its optimal electrical window for too long, the machine literally destroys itself.
So we have this brilliant machine that is incredibly fragile in the face of natural reality.
Completely fragile.
And how do human engineers traditionally solve a problem like that? I mean, we don't try to make the machine itself more resilient. We add a manager.
We do. We build a bureaucratic layer right on top of the machine.
The manager, in this context, I want to pose this philosophical question to you listening. Why is our instinct always to add a boss to a system instead of fixing the system itself? Why do we just inherently assume a system left alone is going to fail?
Well, that is the exact engineering mindset we've inherited. The manager for an artificial leaf is a complex suite of electronics called a maximum power point tracker, or MPPT,
MPPT.
along with a DC to DC converter. Let's look at the anatomy of this traditional setup, because it's wild. You can't just wire the solar panel directly to the electrolyzer.
That'd be too simple.
Right. Instead, you put a microcomputer in between them. This computer has sensors that are constantly measuring the intensity of the sunlight and the current coming from the panel, taking readings hundreds, sometimes thousands of times a second.
It's essentially sitting there with a clipboard, nervously monitoring the sun.
Exactly. Then an algorithm calculates the optimal voltage and current needed by the electrolyzer at that exact millisecond. It then commands a series of solid-state switches in the converter to artificially step the voltage up or down to keep the electrolyzer in its perfect happy zone completely, regardless of what the sun is actually doing.
But wait a second. If a massive dark storm cloud rolls over, there simply isn't enough raw energy coming from the sun to keep the reaction going, no matter how clever the algorithm is, right? I mean, you can't magically invent power out of thin air.
And that is exactly why the manager requires its own external support system, a buffer battery.
Ah, of course.
A battery. The traditional artificial leaf always has to be hooked up to a lithium-ion battery. When the sun is bright, some of the power goes to making fuel, and some goes to charging the battery. When the cloud blocks the sun, the microcomputer detects the drop, instantly taps into the battery, and injects stored electricity into the electrolyzer to keep the chemical reaction perfectly stable.
So we've essentially built a middle manager.
A very anxious middle manager.
And like a lot of middle managers, its entire existence is really just compensating for the fact that the system it oversees isn't actually well suited to the real world. We bolt this entire small brain onto the side of the device.
We do.
And I really want you to think about the cascading consequences of that design philosophy. When you add sensors, microprocessors, complex wiring, and lithium batteries to a simple chemical process, what are you actually doing to the system?
You are multiplying the points of failure. exponentially. This is basic systems theory. Every additional component is a component that can and eventually will break.
Right.
If the irradiance sensor gets covered in bird droppings, it feeds bad data to the computer. The computer sends the wrong voltage, and the electrolyzer degrades.
Because of a bird.
Because of a bird. If a transistor in the DC converter shorts out from humidity, the system dies. If the lithium battery degrades over thousands of charge cycles, which they literally all do, the buffering capacity vanishes and the system dies.
And it's not just about things breaking. I think what the source text really hammers home is that it's about the massive supply chain you've just inextricably chained this artificial leaf to.
Oh, the supply chain is staggering.
The leaf itself might just be some glass, water, and a few metal catalysts.
Wait, what?
But the manager requires silicon mining. It requires multi-billion-dollar semiconductor fabrication plants in Taiwan, global shipping networks, rare earth lithium and cobalt mining for the battery.
Right, you are trying to build this distributed, localized, green energy solution, but you've tethered it to the most centralized, ecologically destructive, and complex industrial supply chains on the planet.
It completely defeats the philosophical promise of the artificial leaf. The dream was a device that sits in the sun and independently sustains itself, like a plant. But we built an artist that is entirely dependent on a micromanager, and the micromanager is dependent on a global logistics network.
Because we view nature's variability as a hostile chaos, and our only engineering instinct is to impose rigid control from the outside to force nature into a predictable box.
Which brings us to the Osaka breakthrough. This is the moment where the script flips entirely, because the researchers in Japan didn't just try to build a more efficient microchip or a longer-lasting lithium battery.
No, they took a completely different path.
They looked at this incredibly convoluted, fragile tower of electronics and basically said, what if we just get rid of all of it? They asked a fundamentally different question. What if the device could regulate itself through its own physical nature?
They pursued what they call battery-free artificial photosynthesis. And to achieve it, they had to move the intelligence of the system.
Move the intelligence?
Yes. Instead of the intelligence existing in an external software algorithm on a microchip, they wove the intelligence into the atomic structure of the materials themselves.
Okay, this is the part where my jaw actually dropped reading the paper. Because it sounds like literal magic, but it's just incredibly elegant, solid-state physics.
It's brilliant physics.
Walk us through the exact mechanism here. If there's no computer, no sensor, and no battery, how on earth does the Osaka electrolyzer know what to do when a cloud passes?
It relies on the natural, unavoidable byproduct of sunlight, which is heat.
Heat? Oh.
Let's think about standard conductors for a moment. Host, what usually happens to electrical equipment when it gets really, really hot?
Well, I mean, my laptop fan starts sounding like a jet engine, and everything throttles down and runs terribly. In standard electronics, heat is the enemy, right? It increases electrical resistance.
Exactly. The atoms in a copper wire, for instance, they start vibrating faster and faster because of the heat. That creates more friction for the electrons trying to flow through. So more heat equals more resistance.
Right, that makes sense.
That is what physicists call a positive temperature coefficient. But the Osaka team didn't use standard conductive metals for the internal circuitry connecting their solar cell to their electrolyzer. They designed the system using specific semiconductor materials that have a negative temperature coefficient.
Negative.
Yes, often called thermistors in other applications. In these specific materials, when they absorb heat, the thermal energy doesn't just vibrate the atoms, it actually excites more electrons into what's called the conduction band.
I want to make sure that the listener is really tracking this because it's the core of the genius here. So in these specific materials, as they get hotter, they don't get more sluggish. They actually become better conductors. Their resistance drops.
Yes. The heat effectively widens the pipe, allowing electricity to flow with much less friction. Now let's map that onto the natural rhythm of a day.
Okay, walk me through a day.
The sun comes up in the morning. As the sunlight grows more intense, two things happen simultaneously. First, the solar cell generates more raw electrical voltage because there's more light.
Right, standard solar panel stuff.
Second, the physical body of the device naturally warms up simply because it is sitting in the sun.
And as it warms up, the internal resistance of those specific semiconductor materials drops.
Exactly, and because the resistance drops, the electrical gates open up, allowing that increased electrical current to flow smoothly into the electrolyzer exactly when it is needed to match the higher light levels.
So the chemical reaction accelerates, producing more formic acid, and the physical material naturally tunes the circuit. And then the inevitable happens. A thick, Dark cloud rolls across the sun.
And the process immediately reverses in perfect symmetry. The light fades, meaning the raw power from the solar cell drops. But at the exact same time, the physical device is now in the shade.
Right.
So it begins to cool down. As the semiconductor material cools, fewer electrons are excited into the conduction band. The electrical resistance naturally rises back up. The pipe narrows.
So it naturally restricts the flow of current, protecting the delicate catalysts in the electrolyzer from experiencing that catastrophic voltage crash you mentioned earlier.
Exactly.
It chokes itself precisely in proportion to the lack of light.
It does. There is no battery storing power. There is no sensor taking readings. There is no software running an algorithm. The shift in temperature is the sensor. The material's resistance is the algorithm.
The intelligence is entirely intrinsic.
Entirely. And the most remarkable part of the EES solar paper is that they took this device out of the pristine, climate-controlled laboratory. They set it up outdoors under the real, unpredictable sky in Osaka, and they just left it alone.
And it worked.
It worked perfectly. It steadily produced formic acid as the sun rose, as clouds passed, and as evening set in, completely unsupervised.
It is exactly like the human pupil. I was trying to think of an analogy for this, and the eye is just perfect.
Oh, that's an interesting way to look at it.
Think about walking out of a dark, air-conditioned movie theater into a blindingly bright parking lot in the middle of summer. You don't have a separate manager sitting in your prefrontal cortex, consciously calculating the lumens of the sun, running mathematical algorithm, and then sending an urgent memo down the optic nerve telling the iris muscles to contract by like 43%.
Right. If you had to process that centrally, you'd be blinded before the signal even arrived.
Exactly. The latency of a centralized system would be disastrous. Instead, the physical response is the adjustment. The excess light hits the eye, and the local physiological mechanism of the iris naturally tightens in response. It is an immediate, unbroken conversation with the environment. It doesn't ask permission from a central brain to protect itself.
That is a phenomenal analogy, and it cuts to the absolute heart of what the author of The Intelligence of Inner Order is trying to articulate. In the old traditional way of building an artificial leaf, the adjustment is an action performed on the device by an outside entity.
Right.
It is an imposition of control. In the Osaka electrolyzer, the adjustment is the device, simply being what it is. It's a property of existence, not a rule that must be enforced from above.
But, I do want to push back on the physics for just a second because the engineering nerd in me is waving a massive red flag right now.
Go for it.
The sun's light drops instantly when a cloud passes.
Right.
The speed of light is the speed of light. But heat takes time to dissipate. If a cloud blocks the sun, the device is still going to be physically hot for several minutes.
Ah, yes. Thermal lag.
Right. Doesn't that thermal lag cause a massive mismatch? If the resistance stays low because the material is still hot, but the solar power has already dropped, doesn't the system crash anyway?
That is the exact engineering hurdle the Osaka team had to solve. And honestly, it's why this paper is such a monumental deal. You're absolutely right about thermal lag. If they just used a massive block of material, it would retain heat way too long and the timing would be disastrously off.
So how did they fix it?
The breakthrough was in tuning the thermal mass of the components. They had to engineer the physical structure to be incredibly thin and thermally responsive so that its rate of cooling closely matched the typical drop-off rate of solar irradiance during cloud cover.
Oh, wow. So they matched the thermodynamic time constant to the optical time constant?
Exactly. They tuned it so the heat bleeds off at the exact same speed the light fades. Now, is it perfect? No natural system is absolutely perfect. But they tuned the material properties closely enough that the device stays safely within the operational window of the catalyst without ever needing that battery buffer.
Okay, that makes total sense. They engineered the physical body to shed heat at the exact rate the reaction needs it to. That is brilliant. And this is where the source text, The Intelligence of Inner Order, really asks us to pan the camera back.
To look at the bigger picture.
Right. The text says the adjustment is the device, being what it is, in conversation with the day. Because this one little lab experiment in Japan, this one electrolyzer, quietly making ant venom fuel while the clouds roll by, it's really a proof of concept for something much, much bigger.
It forces us to look at the massive, bloated, top-down architecture of our entire modern world.
Yes. The text asks us to sit with the shape of this concept. We have built nearly our entire civilization around a deep-seated fear of unmanaged systems.
We genuinely believe that the alternative to central control is catastrophic chaos.
We do. And nowhere is this more obvious than in our energy grids. The electrical grid is the ultimate monument to the manager philosophy.
Let's unpack the grid because it's something we use every second of every day, but we rarely think about how bizarre the architecture actually is.
The electrical grid we have today is essentially the exact same conceptual model Thomas Edison and George Westinghouse fought over a century ago.
Exactly. The fundamental architecture is purely top-down. We build a massive, incredibly expensive centralized power plant, a nuclear reactor, a coal-fired boiler, or a massive natural gas turbine. We generate a staggering amount of energy in one single geographic location.
Right.
But because electricity must be consumed the exact instant it is generated, we have to push that energy outward through a dizzyingly complex web of high-voltage transmission lines, step-down transformers, and substations.
And managing that web requires an almost unimaginable level of imposed control.
Oh, the telemetry is insane.
You have these massive grid control rooms literally looking like NASA mission control, where operators are constantly monitoring demand across millions of... Oh, it's halftime at the Super Bowl, and everyone just opened their refrigerators.
Right, demand spikes instantly.
The operators have to instantly spin up these massive peaker plants to inject more power into the grid,
Right.
or the whole system experiences a cascading blackout.
It is the ultimate expression of what we discussed earlier, imposed intelligence. It requires constant, massive energy just to run the control systems themselves. It requires a vast apparatus of communication telemetry. And it is inherently, fundamentally brittle.
It is so vulnerable to single points of failure.
If a tree falls on a critical transmission line in Ohio, or if a centralized software system gets hacked, or if a transformer blows, millions of people lose power instantly. The nodes at the edge of the network, your house, my house, have absolutely zero agency. We are completely dependent on the central manager.
And it's not just the energy grid. If you really sit with this wondering, you see that this philosophy infects everything we do. Look at corporate structures.
Oh, absolutely.
We have a CEO at the top, a board of directors, and then layers upon layers of middle management. What is the actual purpose of middle management? It's the human equivalent of the MPPT controller.
Right, just regulating the flow.
Its only job is to ensure the nodes at the bottom, the workers are doing exactly what the central authority demands. Because the assumption is that without rigid supervision, the workers will just descend into unproductive chaos.
You see it in centralized economic planning. You see it in traditional educational models where every single student is forced through the exact same standardized testing curriculum at the exact same pace. We are utterly obsessed with top-down imposed order. We assume that complex systems cannot self-organize.
Which brings us back to the sheer terror this Osaka electrolyzer might represent to traditional power structures.
It's deeply subversive in a quiet way.
It is. To trust the material, to trust the intrinsic inner order of a system, means relinquishing the illusion of control. If the nodes in a network, whether they are artificial leaves on a roof, or employees in a company, or citizens in a community, can effectively manage themselves by responding to their immediate local environment, well, the control room becomes obsolete.
The manager is exposed as an expensive, fragile vanity project.
It is a radical decentering. That is the philosophical core of the leaf that needs no manager. If we allow ourselves to take this principle of intrinsic self-regulating order and apply it to broader structures, a completely different arrangement of society begins to emerge.
It's a shift from the fragile pyramid to the resilient forest.
Let's explore that forest. Let's look at the shimmering alternative for a minute.
Right.
Because if this specific leaf machine actually scales up, if we can produce highly efficient self-regulating electrolyzers that don't need microchips or batteries, the ripple effects are just staggering. We talked earlier about the supply chain of the manager.
Right.
If this device works as promised, you sever that entire chain.
The liberation from the centralized industrial complex is profound. If you don't need a controller, you don't need the semiconductor fabs, you aren't held hostage by global silicon shortages.
You don't care if a cargo ship gets stuck in a canal somewhere.
Exactly. If you don't need a buffer battery, you avoid tearing up delicate ecosystems in South America or Africa to mine lithium and cobalt. You bypass the chemical processing plants, the heavy manufacturing, and the inevitable toxic waste of discarding millions of dead batteries. The device becomes remarkably simple to manufacture and deploy.
And because it's simple, and because it regulates itself, it doesn't need to be hooked up to the macro grid. It can sit anywhere the sun shines. And this is where the formic acid aspect becomes so exciting.
The liquid fuel part.
Yeah. Imagine placing a panel of these on the roof of an apartment building in a dense city. Or imagine placing an array of them at the edge of a remote village in the Himalayas. that has never been connected to a national transmission line.
It creates the possibility of true energy independence, not at the macro geopolitical level, but at the hyper-local community level. The fuel, the formic acid, is generated from universal resources: ambient air, water, and sunlight.
Things everyone has access to.
Right. It operates in 10,000 small places simultaneously, creating a distributed web of self-sufficiency, rather than forcing millions of people to depend on one monolithic power plant hundreds of miles away.
Okay, I want to pause and really dig into this because as much as I love the vision, I have to play devil's advocate for a second.
Please do.
This sounds amazing on a sunny day in a moderately warm climate. But what about a neighborhood in Seattle in December? What about a city where the ambient CO2 is high versus a rural farm where it's lower?
Right.
If we decouple from the massive central grid, don't we lose the major advantage of the grid, which is moving power from where it's abundant to where it's scarce? If my local leaves don't get enough sun for a week and I have no grid connection, my house freezes.
That is a highly realistic and necessary pushback. And it's exactly why no serious engineer views this as a magic silver bullet that instantly unplugs the entire world from the macro grid tomorrow. If you live in a high-latitude region with long, dark winters, a local solar-driven system will absolutely struggle to meet baseline demands year-round. However, you have to remember what this device is actually making. It's making a physical liquid fuel, formic acid.
Right. It's not fleeting electricity, it's a stockpile.
Exactly. So in Seattle in July, when the days are long and sunny, your local array might produce a massive surplus of formic acid. Because it's a stable liquid, you just store it in a tank in your basement, just like people used to store heating oil.
Oh, that makes sense.
When December comes and the solar array goes quiet, you just tap into the reserve you built up during the summer. Furthermore, because it's a physical liquid, it creates an entirely new kind of local economy.
What do you mean?
Well, if your neighborhood array has a surplus, but the town over is running a deficit because of a storm, you don't need a multi-billion-dollar high-voltage transmission line to move the energy. You just put the formic acid in a tanker truck and drive it over. It democratizes the transport of energy, turning it into a locally tradable commodity rather than a centrally metered utility.
It changes the fundamental relationship we have with the resources that sustain us. Imagine the psychological shift of living in that world.
It would be profound.
You walk out into your yard or onto your community roof, and your fuel source is just sitting there, working silently. It's not asking permission from a utility monopoly. You aren't paying a monthly tithe to a corporation that has the power to shut off your heat if you miss a payment.
Right.
The anxiety of dependence, that low-level hum of vulnerability we all feel living at the end of a long, fragile wire, it just evaporates.
You transition from being a passive, dependent consumer into an active participant in a resilient local ecology. When a community controls its own physical fuel supply, they are insulated from global shocks.
Yeah. If a geopolitical conflict chokes off the global oil supply, or if a cyber attack takes down a regional power grid, the local formic acid array doesn't care. It just keeps quietly responding to the sun. The shift in power dynamics, political, economic, and social, would be epochal. It's incredibly intoxicating to think about. It feels so clean, so inherently right.
It does.
But, and here is where we have to gently pump the brakes. The source text, the intelligence of inner order, and really our whole mission for this deep dive require us to return to the present reality.
We have to let it rest.
Exactly. It is so easy to let this utopian vision harden into an expectation or a demand. We want it now. But that's the exact opposite of a wondering held open.
Yes, we must ground this. None of this is promised. The text is very clear about the realities of scientific development. The Osaka electrolyzer is an elegant, profound breakthrough, but it is a lab prototype.
Let's talk about those realities. What are the actual hurdles keeping this off my roof right now?
Well, efficiency, for one. While the self-regulating mechanism works beautifully, the overall conversion efficiency of sunlight to formic acid in these early prototypes is likely still quite low compared to mature commercial technologies.
Okay, so it works, but maybe not fast enough yet.
Right. Furthermore, the specialized negative temperature coefficient semiconductors and the specific catalysts used for the chemical reaction, they often rely on rare earth metals or complex fabrication processes that just haven't been scaled up for mass manufacturing. Taking a device that works perfectly at the scale of a few square centimeters in a lab and scaling it to square meters for a roof while maintaining that perfect thermodynamic balance, that is a monumental engineering challenge that will take years, if not decades, to solve.
And honestly, it might never be solved.
Exactly.
It might remain a beautiful, isolated laboratory curiosity, and that is okay.
It has to be okay.
We are not sitting here today predicting an inevitable tech revolution that will sweep the globe.
Yeah.
What is real today is very small, very specific, and deeply profound. A group of researchers proved that a machine can maintain perfect internal equilibrium without an external brain, simply by being what it is.
We are just admiring the shape that this invention points toward. Think about the actual green leaf on the tree outside your window right now.
Okay.
It never had a 5-year plan. It doesn't have an ego or a board of directors or a microchip. It simply engages in a quiet, unbroken, physical conversation with the sun, the air, and the water. It just is. And the being is enough to sustain it.
The being is enough. We don't need to force this one laboratory experiment into a definitive 10-point policy roadmap. We don't need to demand that it replaces the grid tomorrow. The spark itself is enough.
It illuminates the room for a moment.
It shows us that our entire philosophy of imposed control and micromanagement is just a choice, not a law of nature. It shows us a completely different way of thinking about engineering, and then it returns to rest. It allows us to just hold the possibility in our minds without strangling it with expectations.
So let's briefly recap the rather vast journey we've been on today.
We've covered a lot of ground.
We really have. We started with the dream of the artificial leaf, the quest to convert ephemeral sunlight and ambient carbon dioxide into a tangible, physical liquid fuel like formic acid.
To the ant venom fuel.
Right. We examined the fatal flaw of intermittency and how humanity's default instinct was to bolt on fragile, complicated, supply chain-heavy managers, controllers, and batteries to force the machine to survive in the real world.
And then we looked at the elegant rebellion of the Osaka team. They eliminated the manager by using specialized materials whose physical resistance drops as they warm up in the sun, creating an intrinsic, self-regulating feedback loop.
A machine that acts like a pupil dilating, bypassing the need for an external boss entirely.
And finally, we followed that thread outward. We challenged our deeply seated societal fear of unmanaged systems, from centralized power grids to corporate hierarchies, and explored the shimmering possibility of a decentralized, hyperlocal world that governs from within.
It has been a deeply rewarding exploration, and I really want to acknowledge you, the listener, for sticking with us through the complex chemistry of electrolysis, the solid-state physics of semiconductors, and the sociological implications of grid architecture.
It's a lot to take in.
It is. It requires a certain intellectual flexibility to explore a concept like this deeply without immediately demanding to know the return on investment. To appreciate the profound elegance of a machine that acts like a leaf is a valuable exercise in expanding how we think about what's possible.
So as we wrap up this deep dive, we're going to leave you with a final lingering thought, a little piece of homework for your own life, if you will.
I love this part.
We spent an hour looking at a machine that found its own perfect balance simply by being what it is, in quiet conversation with its environment. What I want you to explore on your own is this. Zoom out from the technology and look at the structures you operate within every single day.
Your workplace, your community.
Maybe even your own habits and family dynamics. What rigid, overmanaged, constantly supervised systems in your own life might actually function beautifully, perfectly if they were finally allowed to self-regulate from within, rather than being exhaustingly controlled from above.